In this video lecture, we shall learn diatomic vibrating rotator. In infrared spectroscopy, a diatomic vibrating rotator is a molecule that has both rotational and vibrational motion. The energy of a vibrating rotator is a sum of the vibrational energy and the rotational energy. Since changes in rotational energy levels are typically much smaller than the changes in vibrational energy levels, the changes in rotational state are said to give fine structure to the vibrational spectrum. The rotational spectra cannot be separated from the vibrational spectra. Any diatomic molecule will have rotation as well vibration at normal temperature. Energy levels will exist for both vibration and rotation. A typical diatomic molecule has a rotational energy around 10 centimeter power minus 1, whereas a vibrational energy separation lies around 3000 centimeter power minus 1, since the energies of the two motions are so different. Hence, at a first approximation, it is considered that a diatomic molecule can execute both rotations and vibrations quite independently. This approximation is known as Born-Oppenheimer approximation. The rotational energies are much smaller compared to vibrational energies. The rotational bands appear as a fine structure on the vibrational band. Assuming that the combined rotational vibration energy is simply the sum of separate energies of rotation and vibration, excluding electronic energy. So we have E total, which is equal to the sum of E rotational and E vibrational. In terms of wave number, the equation 2.25 can be written as the wave number which depends on J and nu, which is equal to the wave number of J plus wave number which depends on nu. This is measured in terms of centimeter power minus 1. So we know that the expressions of corresponding wave numbers are given by. So this is the corresponding wave number for the rotational energy, which is equal to dj j plus 1 minus dj squared j plus 1. So j is the quantum number, which has the value 0, 1, 2, ... And similarly, the wave number for the vibration energy is given by nu plus 1 by 2 omega e, and this is equilibrium oscillation frequency, minus nu plus 1 by 2 whole squared xe, which is nothing but unharmonicity constant, multiplied by equilibrium oscillation frequency. So here nu equals 0, 1, 2. Substituting the values of Ej and E nu from equation 2.27 and equation 2.28 we have, and this is for rotational energy, rotational wave number, and this is for vibrational wave number. So we have added these two with the corresponding rotational constant and vibrational constant. We are going to use selection rules for the combined motions, which are given as del nu, which is equal to plus or minus 1, plus or minus 2, plus or minus 3, and del j equal to plus or minus 1. At special circumstances, del j equal to 0 is allowed. Now we are going to consider the transition from nu 0 to nu, which is equal to 1. So we are going to consider this. So we can have del E j comma b, which is equal to the higher level minus lower level. So now we are going to use this equation 2.29 and use as substitute nu equals 1 here and nu equals 0 here. So there's a mistake here. This is nu equals 0. In equation 2.31, there's a mistake. See, this is nu equals 1 minus, here it is nu equals 0. And of course here j dash is there, here j double dash is there. and this is for the lower state, and this is for the higher state. So this is for the ground state, this is for the first excited state. Now let us subtract this one. So this equation 2.29 becomes as per this. So we have nu equals 1. So this becomes B times J prime J plus 1 minus J double prime. This is for the lower state. So J double prime plus 1 minus D J dash squared J dash plus 1 whole squared minus J double prime squared times J double prime plus 1 whole squared. And this is for the vibration energy. As I said earlier, this is for nu which is equal to 1, and this is for nu which is equal to 0. So as I said, there's a mistake here, nu equals 0. So 1 plus half mean oscillation frequency minus 1 plus 1 by 2 whole squared xc omega e minus 1 by 2 omega e minus 0 plus 1 by 2 whole squared xc omega e. So let us simplify the second term first. So 1 plus 1 by 2 will give us 3 by 2, and here it is 3 by 2 squared, and here 1 by 2, and here it is 1 by 2 whole squared. So the second term becomes exactly like this. So we have now 3 by 2 omega e minus 1 by 2 omega e. This is 1.5, this is half, that will give us omega e. So omega e. And this is minus 9 by 4 xc omega e. This is minus minus plus, so 1 by 4. So that will give us 8 divided by 4. 8 divided by 4 will give us 2. So minus 2 xc omega e. This term let it be like this. So we have now pulling omega e out. So that will give us 1 minus 2 xc omega e plus this term. So this term let it be like this. So this is equation 2.34. This is difference in wave number. Now we are going to apply the selection rule. First we shall apply del J equals plus 1. If del J equals plus 1, it implies that J prime minus J double prime which is equal to 1. Therefore J prime which is equal to J double prime plus 1. And let 1 minus 2 xc omega e, we are going to keep this omega naught. And this omega naught is a frequency which we call this as band origin or band center. The wave number for transition between fundamental vibration energy level, what we call this as pure level. The value of B is the same for upper and lower rotation energy levels. What we call this as band origin or band center. Now let us substitute this expression, that is J prime which is equal to J double prime plus 1 and 1 minus 2 xc omega equal to omega in the equation 2.34. So we have instead of this we are going to substitute omega naught. So we have substituted omega naught here plus D. Instead of J prime, you just substitute J double prime plus 1. So wherever you find J prime, you substitute J double prime plus 1. So that will give us J double prime plus 1, J double prime plus 1 minus this one, this term already it is J double prime. So J double prime plus 1 minus D times this whole term. Now this omega naught, let it be like this. Just you pull J double prime plus 1 out. So that will give us, see here you are going to pull J double prime plus 1 out. So J double prime plus 1. Here also we have J double prime plus 1 out. So common J double prime plus 1 out, that will give us, the remaining term will be J double prime 1 plus 1, that will give us 2, and here it is minus J double prime. So minus J double prime, and this J double prime and this minus J double prime will get cancelled. The 2 will be there. I have pulled this 2 out. So 2 will be J double prime plus 1. Coming to the expression for D, here D, you pull J double prime plus 1 whole squared out. So that will give us this term. The remaining term will be J double prime plus 2 whole squared, and here the remaining term will be minus J double prime squared. And of course you just expand this one, A plus B whole squared formula. So we have J double prime squared plus 4 J double prime plus 4, and this term minus J double prime squared, and this term will get cancelled. We have 4J double prime plus 4. You pull 4 out, so that will give us 4 times T J double prime plus 1 whole square J double prime plus 1. Multiplying these two will give us J double prime plus 1 whole cube. So this is the expression for del E nu, and what we call this, we operate selection rule as del J plus 1, and this is known as R branch. So we are going to apply this if the selection rule is del J plus 1, and this branch is known as R branch. That is, lines corresponding to the selection rule del J plus 1 are called as R branch. Now we are going to apply the selection rule del J minus 1. So we know that the selection rule is nothing but del J plus or minus 1. First we have applied for plus 1, and next we are going to apply for del J equals minus 1. So if del J equals minus 1, it implies that J prime minus J double prime, which is equal to minus 1. Therefore, J double prime equal to J prime plus 1. So wherever you find J double prime, you substitute J prime plus 1 in equation 2.34. As usual, we are going to substitute 1 minus 2 xc. Omega is nothing but omega naught. So this becomes omega naught plus B times J prime plus 1 minus J prime plus 1 plus J prime plus 1. So wherever you find J double prime, we have substituted J prime plus 1. See, J prime plus 1, and minus B, and this is J prime squared, J prime plus 1 whole square, minus this is your J double prime squared. So this becomes J prime plus 1 whole square, 1 plus J prime plus 1 whole square. Now we can pull J prime plus 1 out. So you can just pull J prime plus 1 common in this term. So we have J prime plus 1 out. So the remaining term will be J prime minus the remaining term will be here J prime. 1 plus 1 is nothing but 2. So plus 2. And here you can pull J prime plus 1 whole squared out as common. So D J prime plus 1 whole squared common out. So we have J prime squared minus you have J prime plus 2 whole squared. So now J prime minus 2J prime, here it is minus 2 because minus is there. So minus 2. This J prime and this J prime will get cancelled. We have minus 2, you pull it out, so that will give us minus 2b J prime plus 1. And here we just expand J prime plus 2 whole square. So we have J prime squared minus 4J prime minus 4, and these two terms will get cancelled. We have minus 4J prime minus 4. You pull minus 4 out, already one minus is there. So that will give us plus 4D J prime plus 1 whole square. Here it is J prime plus 1 is there. So we have J prime plus 1 whole cube. And this is the complete expression for your P branch. Already we studied for R branch. That is for del J equal to plus 1, and here it is del J equals minus 1. This will give the lines corresponding to the selection rule del J equal to minus 1. What we call this as P branch. Now substitute M equals J prime plus 1 and M equals J double prime plus 1 in equation 2.36 and equation 2.37, and we can combine P branch and R branch as in one equation. So we have this expression, equation 2.38. So we have plus or minus 2bm minus 4dm cube. So it takes positive R branch and negative P branch. And suppose we are going to consider D is very, very small. Then we can have this expression, change in wave number, which belongs to both P branch and R branch, which is equal to omega naught plus or minus 2bm centimeter power minus 1. This equation represents the combined vibrational rotational spectrum, and this will have both P and R branches. Each consists of equally spaced lines, which is nothing but 2b. The frequency omega naught is usually called the band origin or band center. Evidently, it will consist of equally spaced lines, which is nothing but 2b on each side of the band origin. But since m is not equal to 0, the line at omega naught itself will not appear. The separation is 2b. The branch appears on the low frequency side. Lines to the low frequency side omega naught corresponding to negative negative m, that is del J equals -1, are referred to as P branch, while those to the high frequency side will have positive m, that is del J equals +1, are called R branch. Other branches are given according to the selection rule. Suppose if del J equals -2, what we call this as branch name is nothing but O branch. And del J equals -1, just now we have studied this is P branch. If del J equals 0, we have Q branch. Del J equals +1, we have R branch. And del J equals 2, we have S branch. Vibration rotation spectrum of a diatomic molecule allows one to determine the band center omega naught and B rotation constant from the spacing between lines. From B, one can calculate the bond length. Of course, if B is known, bond length can be calculated. And from omega naught, one can calculate bond force constant, which is nothing but K. When del J equals +1, the rotational quantum number in the ground state is 1 more than the rotational quantum number in the excited state. We call this as R branch. When del J equals -1, the rotational quantum number in the ground state is 1 less than the rotational quantum number in the excited state. What we call this as P branch. The selection rules for these two motions are given as del J equals ±1 and del nu equals ±1 and 2, ±2. As for the diatomic molecules that have angular momentum are not equal to 0, so del J equals 0 ±1, and when del J equals 0, in this case, a new branch is generated such as Q branch, and the rotational quantum number in the ground state is the same as the rotational quantum number in the excited state. And when del J equals 0, what we call this lines corresponding to Q branch. The rotational levels are sketched in the figure, which we are going to see after the 2 or 3 slides in the figure. For two lowest vibrating levels, nu equals 0 and nu equals 1, along with PR, P and R branches. This is the conventional notation for such spectra. There is, however, no attempt at scale in this diagram, since the separation between the neighboring J values, in fact, only some 1/1000 times of that between new values. Note that since the rotational constant B in equation 2.39, here it is 2.39, is taken to be the same for all J and nu. The separation between two levels of given J is the same in nu equals 0 and nu equal to 1 states. If D is included in this expression, equation 2.39, we have neglected D. Suppose if D is included and this expression becomes, the wave number expression becomes, change in wave number expression becomes omega naught plus 2Bm minus ODMQ, which is measured in centimeter power -1, where m equals ±1 ±2 goes on. We know that the values of B will be around 10 centimeter power -1 or less. For D, it is some 0.01% of B, so very, very low. And it is obvious that D is negligible to a very high degree of accuracy. However, the unharmonicity factor should not be negligible. Xc should not be negligible because it affects not only the position of the band origin, since omega naught equal to 1 minus 2Xe omega E, but by extending the selection rules to include del nu equals ±2 ±3 goes on, also allows the appearance of overtone bands having identical rotational structure, and this is for overtone ±2 ±3. First overtone, second overtone goes on. In addition, from the band centers, one can calculate the equilibrium frequency omega E and the unharmonicity constant Xe. And this figure is shown for the rotational energy levels of the vibrational states nu equals 0 to nu equals 1. And this is for nu equals 1, so nu equals 0, and this is for nu equals 1. And the rotation vibration transition of a diatomic molecule. And this is for the lowest state, J double prime equal to 0, 1, 2, 3. And this is for the first excited state, the J prime which is equal to 0, many levels are there. And these horizontal lines are called vibrational energies. And the transition is nothing but rotation energies. And this is for left hand side which is for del J equals -1, right hand side which is for del J equal to +1, and this is for R branch and this is for P branch. Left hand side is for P branch, right hand side is for R branch, and at the center where del J equals 0, this is for Q branch. And what is the selection rule? So look at the selection rule. It is del J equals -1. We'll have the first one. Let us see how it goes. So we have, see, 1 to 0, -1, and 2 to 1, so -1. See here, 2 to 1. And next one will be 3 to 2. See, 3 to 2. And similarly here it is 4 to 3. And here it is for +1 we have 0 to 1. And here it is 1 to 2. See, and goes on. We should note that taking B to be identical in the upper and lower vibrational states is a direct consequence of Born-Oppenheimer approximation. Rotation is unaffected by the vibrational changes. And the difference between these two is nothing but 2B, here also 2B. Difference between these two, P and R branch, is nothing but 4B. And detailed graph is shown here. And this is for, as I said, this is for nu equals 0. Many levels are there for J prime, J double prime. And this is for nu which is equal to 1. Different levels are there for J prime, 0, 1, 2. And as I said earlier, at the center we have the selection rule del J equals 0. And this is for Q branch. And this is nothing but your band center or band origin. And difference between these is nothing but 2B. Here also 2B. The difference between the first P1 and R0, and this is nothing but 4B. The lines with the maximum intensity may not be the first one in the P and R branches, and is due to the degeneracy of rotational states. Taking degeneracy into account, the maximum population and hence the maximum intensity of the transition occurs at J value. So we are going to find out now the maximum population at J level. Maximum population at J level is given as J, which is equal to root of KT divided by 2BHC minus 1 by 2. Now we know that M equals J plus 1. So this equation 2.40 becomes M equals, so here it is plus 1. Okay, instead of M you substitute J, instead of J you substitute M minus 1. And minus 1 goes that side, so that will become plus 1. Plus 1 minus 1 by 2 will go plus 1 by 2. So M equals root of KT divided by 2HB plus 1 by 2. Now substitute this expression of M in equation 2.39. So we have equation 2.39 here. You substitute the expression for M here. So we can get the change in wave number with the maximum intensity, which is given as omega naught plus or minus 2B root of KT divided by 2HCB plus 1 by 2, where the positive sign for R branch and negative sign for P branch. Now let us calculate the separation between the two maxima in the P and R branch, which is given as this minus of this. So we have the separation between two maxima del E nu, which is equal to this minus of this. So that will give us 4B times root of KT divided by 2HCB plus 1 by 2. Now you multiply 4B inside. First let us multiply 4B to the second term. So 4B by 2. 4B by 2 will give us 2B. Now 4B multiplied by root of KT by 2HCB. What I am going to do is, I am going to multiply 8B inside, here 8B in the numerator, and I am going to multiply same 8B in the denominator. So that will give us under root 8B KT divided by, here already 2 is there. So this becomes 16HCB squared. I am going to pull 16B squared out. So that will give me 4B. And this 4B and denominator we have 4B, we have pulled out. That will get cancelled. The remaining term will be root of 8B KT divided by HC plus 2B. Now, if you are going to consider B is very, very less than that of del E nu. then we can neglect this B. We can neglect this B. So now squaring this term, that will give us 8B KT divided by HC. This is equal to del E nu squared. So from this expression, one can get the value for B, which is equal to HC times del E nu whole square divided by 8 KT, provided B should be less than that of del E nu. This procedure offers to estimate the rotational constant B. Here C is expressed in terms of centimeter power -1.